Yes. Sir, shall we start?
Yes, you can start now.
Yeah, please. My heartiest greetings to one and all present here. This is Dr. S. Salamilu, member of Pi Mathematics Association. We feel elated to gather wonderful people like you on the eve of National Mathematics Day. Pi Mathematics Association takes great pride and pleasure in welcoming you all. This lecture series is organized to pay our respect and honor to Sri Srinivasa Ramanujan, the man who knew infinity, for his centenary remembrance year, as well as commemorating his 133rd birth anniversary. Pi Mathematics Association, a registered trust, has been organizing and conducting many events which give us knowledge about mind regenerating and explorative concepts in the field of mathematics. This time, the event is to be held for 2 days, today and tomorrow, as a motive of keeping our minds enthusiastic and energetic. We'll be having 3 speakers a day for 3 different sessions. We have with us eminent professors and mathematics enthusiasts from across the globe in this single occasion. Now, I request Mr. R. Shankar, trustee of Pi Mathematics Association, to give us a glimpse of the association. Please, sir.
Thanks, Alamali Madam, giving a control over to me. It's my honor, to talk about Pi Mathematics Association. The association formally started in the year of 2007. It's almost, it's a happy moment to look back our 13 years journey. It's one of the fine day, in along with Professor Sivaraman sir and other students, we were having a chat. That how do we take this knowledge, to next generation? That was a topic. Dr. Sivaraman was so passionate about taking the maths to the larger community, students, parents, and teacher. Then he was talking about. So the one of the thought process was, why don't we start an organization, especially that focus on mathematics? So that day, that leads to the start of Pi Mathematics Association. See, when we started this association, the primary objective was to remove maths from here among the society. Then also we serve who deserve. If you look at our logo itself, you can see we serve who deserve. So the tools which we adopted are primarily, we started with guest lectures across India. Especially, we started with schools and college. Then also we use the methods like charts and model-based teaching, typically, to popularize the subject. Then, we also, the next step was we also, set up some few maths labs across the colleges in Chennai. Then we also decided, how do we spread maths further? Why don't we, document and publish some books? So every year we thought at least we should publish one book. Almost we have published 16 books, which are both in state language Tamil as well as in English. They basically covers various methods have been used, like story based and some crime novel based and environment based. Then also what we did is these books are not only contributed by Dr. Sivaraman sir, also there are other teachers who are part of the Pi Mathematics Association also contributed to this. So Sangodaya is one among them. There are individuals teachers like Vijay Kumar, Balaji, Yogesh, Bojarajan, Manoj. So those are the people who contributed on building articles, also taking a guest lectures across the schools and colleges. So our if you look at one of the method what we followed is we should keep writing the articles about mathematics in various leading magazines like Hindu, Dinamalar, Chutti Vigadan, maybe various methods like quiz, puzzles, and contents. So apart from the teaching space, we also support financially backward as well as deserving students on the school fees. We do this once in a year. So this has been supported by the community itself. There are a lot of volunteers who support Pi Mathematics Association who contribute to the school students. See, also, Pi Mathematics Association We every year we wanted to conduct one induction program for college students. We have been doing consistently for a couple of years. Since this year, due to COVID situation, what we did is we did this virtually via a webinar. Again, so we are very active in the social media outreach as well. All our programs and articles have been regularly circulated via Facebook and YouTube, and all the trainings lectures are documented over here. So let me logically conclude the briefing about the pi mathematics and hand over to the host. Thank you.
Thank you, sir. Now I request Professor R. Shivaraman, sir, founder, Pi Mathematics Association, to give an introduction about our famous speaker for this session. Please, sir.
So thank you, madam. First of all, I feel very happy and privileged to have this lecture series conducted by Pi Mathematics Association. My first and foremost thanks to all the professors who had been readily accepting our invitation for presenting their lectures. Beginning with the first lecture, I'm here to introduce today's first speaker, Professor Benoit Rittaud. I hope I had spelled correctly. Maybe he can correct me if I'm wrong. Um Benoit, it was it's not new to Pi Mathematics Association. He was already uh, known to us. He came a couple of years back to India, and when we asked about his credentials to introduce before the audience, he was just writing 3 to 4 lines. That shows how simple he was. See, usually great mathematicians and great people don't say much about them. Their words doesn't speak, but their actions speak. In that regard, I think Benoit Rittaud was a classic example because he hardly gives anything about him, and most of the available data in the internet was unfortunately written in French, which we cannot understand. So in either way, we don't have any chance to know more about him. But with little whatever we know, we are just introducing. If there is anything vitally missed out, Professor can pardon us for not saying so. With what little I know, I can introduce Professor. See, usually when you see there are great professors like Benoit Rittaud, who was a teacher who was very passionate about teaching. He usually told me that he loves teaching. So there are many good teachers, of course, throughout the globe, but there are only few teachers who do go beyond their teaching job. Like he was a teacher, he was a researcher, he was math popularizer, he was a multifaceted personality in the sense that he could mold into any character that you want to. And I think he has done so many little projects and published so many videos. Maybe he can throw some light on that videos that he had produced, so that if something is new to them, we can also share through our channel, so that others can also view and get benefit from that. He was working as professor at Sorbonne, Paris Nord University, and as I told, he published so many books, interesting books, and he came in 2018 March during World Pi Day occasion, March 14th, but not exactly on March 14th. I hope it should be on March 18th or 19th or someday near to the week of Pi Day. We released a book published by Pi Mathematics Association titled "Cracking Crimes," and I know he was very excited to see the book, and he mentioned me that he has also written a similar book. I don't know whether it's in English or in French. Maybe he can also say something about that. And I request Professor to just say a few words after his talk about what he has done to in the exposition of mathematics, and apart from his talks, what books he has written, because in that aspect we have don't have any much clear idea about that, but I know he had contributed a lot. So in this aspect, we have brought a person who not only just do research and go off, but care for community, mathematics community, care for students, and taking to them the real beauty of mathematics. So in that regard, we are very lucky, and he had been to India twice, and we have planned to bring him here also. He was agreeing to come here during this year also, but due to this pandemic, unfortunately, no one could go away or come here. So, but anyway, we are fortunate enough to have him here today to present his wonderful lecture. The title itself is very exciting because one of the aspects that made Ramanujan very strange among others is to see that when he claimed that 1 plus 2 plus 3 up to something up to infinity sum is minus 1 over 12, because sum of positive numbers is a negative answer that is practically seem to be absurd. So probably Professor will throw more light on this. With this remarks, I invite Professor Benoit to present a talk. Sir, you can talk, sir. You can start.
Is it okay now? Can you hear me?
Yes, sir. It's visible. Yes.
Sorry, maybe I have a little problem in my internet connection. So good afternoon, everybody. I'm very proud to be with you, even if it's not for real. And as Sivaraman said, it's a shame that we cannot meet for real. But I really much enjoyed my two trips in India in 2 years ago, 5 years ago. It was a great moment, and it's a pleasure for me to live it again, even if it's by indirect ways. And I'm also very pleased, not only because I really enjoyed my trip in India, but also to be here to speak about one of the greatest mathematician ever, which is Srinivasa Ramanujan. Sorry for pronunciation. So Ramanujan is a special man in history of mathematics, because it's in general mathematicians are people that can be. Well, you can see when a child is good in mathematics. It's quite easy in general, at least here in France. We have, but I suppose that it's the same almost everywhere. Well, we have scholar systems that allows easily to see people who have some skills in mathematics. And Ramanujan is exception because, we have, he was a self-made man, kind of self-made mathematician, and became one of the most brilliant mathematicians of his century. So it's a kind of exception, and he is also an exception in the history of mathematics, because his way of seeing mathematics was not exactly the standard way. Because in general, mathematicians like to be very precise and have both intuition and rigor to prove what they have in their minds. And Ramanujan was developed especially his intuition, and he was more a man who feel mathematics than who felt mathematics, and more than he proved them. And as for me, the case of the strange sum, the very strange sum written here, 1 plus 2 plus 3 plus 4 plus etc., is a quite significant example of this. Standard proof, and probably knew exactly what he was meaning with it. So, if I can, sorry, there is a kind of, so maybe yes. So, of course, the general idea is that when you add up all integers from 1 to infinity, it's very strange to imagine that this could be equal to minus 12th, because, of course, we have integers, positive integers. So when you do 1 plus 2 plus 3 plus 4, etc., of course, the number are getting bigger and bigger. So if you take one coin, well, plus 2 coins, plus 3 coins, it's very difficult to imagine that it could end up with a negative number, not even an integer number, but a negative rational number. So how can it make sense? And when Ramanujan proposed this equality, wrote it explicitly, he first wrote it on his notebook, his famous notebook he wrote his mathematics, and then he wrote it to the famous British mathematician Godfrey Hardy in his second letter to him, written in February 1913, the 27th February 1913. And at the time, Ramanujan already wrote a first letter to Hardy. The first letter was to introduce himself to Hardy and to say him that, well, you don't know me, but probably I have some mathematics to show you, and I know that you're a big important mathematician, so maybe you could find some merit on what I'm doing on myself in India. And Hardy already wrote him back several days after, and then Ramanujan, in his second letter, wrote again about mathematics. And in this letter, we can read this very equality, 1 plus 2 plus 3 plus 4, etc., equal minus 1 over 12. And of course, Ramanujan understood that this would be this would appear very strange to Hardy. And if I tell you this, so about this equality, if I tell you this, you will at once point out to me the lunatic asylum as my goal. So he knew perfectly that it was very strange, of course, and that it would have to be proven before accepted. What I think it's interesting in this letter is just after the mention of this equality, he wrote something completely different, and which goes like this. So what I now want at this stage is for eminent professors like you to recognize that there is some worth in me. I am already a half-starving man. To preserve my brains, I want food, and this is now my first consideration. Any sympathetic letter from you will be helpful to me here to get a scholarship, either from the university or from the government. That means that, as probably most of you in India already know, we have in this letter both aspects of the life of Ramanujan's life. First part is a mathematician, a brilliant mathematician with an incredible intuition. And second, a man whose life was very difficult at the time, and whose first preoccupation was, first consideration was simply to eat. And it's difficult for us mathematicians to imagine that, because usually, again, in the history of sciences, when you think about mathematicians in general, there are in universities, there are important men or women, and they don't really have financial problems. We don't hear about that very often. And here in France, we have another mathematician a little like this, is Évariste Galois, which is not the very same example. More the Norwegian Niels Abel was like this. But in general, it's not the case. So again, quite not only, well, Ramanujan was not only a mathematician, but also really a human being with a special life and interesting in itself. But probably you know all of this very well, of course. So how about the equality 1 plus 2 plus 3, etc. Equals minus 1 over 12? He wrote it also in his notebook. So it's written like this to explain. And what I would like to do now is to explain his point of view about it. How did he obtain this equality? And so first he defined a number C, which is the sum of all integers. So this is this very number, if I can speak like that, which he wants to prove that it is equal to minus 1 over 12. And then he consider 4 times C. So this gives him 4 plus 8 plus 12 plus 16. And then he do some mathematical trick to operate on this very value C. And the first trick consists in a shift in the numbers written for C. The shift consists in, well, this slide here, to make, to put the 4 below the 2, the 8 below the 4, the 12 below the 6, the 16 below the 8, etc. And then, so it's the same value, but written differently. The aim is to subtract C and 4C. So C minus 4C is simply 3C, minus 3C, of course. And in the right, we have 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7, etc. It's, well, sorry, I put this, but I cannot remove the arrow. So it's very simple to do the calculation column by column. The first one goes down and change. Plus 2 minus 4 is minus 2. 3 alone gives 3. 4 minus 8 gives minus 4. 5 alone gives 5, etc. It's easy to see that. Minus 3C from this calculation is the alternate sum of integers. 1 minus 2 plus 3 minus 4, etc. So this is what you can see written on top, on the picture of Ramanujan's. He does not explain why you write this, but he writes simply that this alternate sum 1 minus 2 plus 3 minus 4, etc. is simply equals to 1 over 1 plus 1 square, which is 1/4. He does not elaborate on this, so we have to look more deeply to understand why he wrote this. It's possible to do it with a power series. It's a kind of elementary play on words, if I can say so. Write some power series and extend its values, and we can get it in some way. But here we can try to provide a simpler explanation to get this value for minus 3C, and a simpler way to get it is to write this alternate sum of integers plus 1 minus 2 plus 3, etc. by a number, say S, and then with the shift of all the numbers, putting the plus 1 below the minus 2, and etc. Then a third time you write S with, again, a shift. I think the shift is wrong here. I put so sorry, maybe I will show you another one. I made some mistake. it's a mistake. It's not the one. It's not the right one. Sorry for this. No, not this one. So I will show you a better one, which is more true. It's not the one I wanted to show, but it's okay. So here is the good one. Sorry for this. So you see the right calculation. We put 4 times the same value s, but with some shifts. So the first one is as usual. The second one is the same as the one I wrote before. Is the same as the second one, and the fourth one is with one more shift in the right. And then we add up all these same values s. So s plus s plus s plus s is 4s. And in the right, we can see column by column that every number cancel out, but the first one, the plus one, the initial plus one remains. And then we have -2 plus 1 in the second column, which is 0. Then +3 -2 plus 1 is 0. Then in the fourth column, -4 plus 3 -2 is 0, etc. Forever. So the value 4s is 1 plus 0 plus 0 plus 0, etc. And of course, well, so now let me go back to my initial things. So sorry, this is in the left. This is the wrong one. Okay, the third s and the fourth s should not be shifted as much as this one. There should be one shift less for both of them. But eventually we get 4s is equal to +1 plus 0 plus 0. So thus we would like to write s equal 1/4. And remember that s was corresponding to -3c. So -3c is 1/4. And so c, the initial expression, would be equal to -1/12. Which is, of course, very disturbing. And to obtain this, we had to do what is said to be in different contexts a suspension of disbelief. That means that forget everything that you know in mathematics, forget that rules are what they are, and try to try to operate, try to imagine. It is probably like this this way that Ramanujan used to go into this. Of course, none of what is written here is correct in the standard way of doing mathematics. Even the first line, c is 1 plus 2 plus 3 plus 4, it's already a problem. Because we should not allow ourselves to write anything like that, because this would imply that c for the sum of the integers could be a number. It suppose that we would be as we operate in usual expressions. And this is wrong, and we know from the beginning that this is false. This is not allowed. But sometimes in mathematics, we have to, in some way, break the rules, go beyond the rules to invent new things. And the most famous example of this is the invention of complex numbers. At some times, it was in the 16th century, mainly the 16th century algebraists in Italy, mainly wanted to solve some equations, polynomial equations of degree 3. And they invented the methods to do so. And sometimes in the applying the formulas, they had to wrote to apply correctly the formula. They had to wrote something that would correspond to the square root of -1. That means a number such that when you multiply it by itself, you get the value -1. And of course, at the time, it was not possible because of the classical rule of signs, which was already known at the time, that when you multiply two numbers, the result is always positive, because minus times minus is plus, and plus times plus is plus. It's the usual rule of signs we all learned about in school. And so we cannot imagine a number which would give -1 when multiplied by itself. It's not possible. So if it became possible, it is only because at some point mathematicians like Spombalis, Cardano, and so on, who said, okay, this is not allowed, but I do it still, and I will invent a new framework in which this will be not only practical to get some results, but also really true and mathematically true. And provided, this is the invention of complex numbers, and which is nowadays the fundamental field for algebra. So something which was at a time impossible, mathematically speaking, became one of the very foundation of all mathematics. But of course, this is not kind of permission to do what we want without being precise. And also after this idea, this suspension of disbelief, after this way of doing things without too much rigor and too much and allowing us different things, there is also a point in which we have to let the precision come back. And for example, for complex numbers, it was not enough to decide that, well, we're going to consider a new number which corresponds to the square root of -1. And as you know, this would have given a lot of problems in mathematics without precision and without stronger foundations, because in the complex field, as we know, the -1 has two roots, not only one. And this is what we write now, I and -I, okay, as any number, any positive number has two square roots. This is true also for -1 in the complex field. So in the beginning, the first mathematician only wrote the square root of -1 and used it without too much consideration for its precision. But at some point, it hurted back. And they had to go deeper into this and say, okay, we're going to allow us things like that, but the suspension of disbelief is not what we want. At some point, we have to remember that precision and proof and clear definitions of what we consider is necessary. And for example, here, if we use all the calculation I've made just before on this kind of calculation without without being careful, then we could easily get some impossible results. For example, consider this operation. I consider again the value c, which is the sum of all integers. And I just want to do the same kind of calculations I've already made just right now. What will happen? So I consider 2 times c and c. So 2c is 2 plus 4 plus 6 plus 8 plus 10, etc. It's on the first line. And then I subtract c, which is 1 plus 2 plus 3 plus 4, etc. And the only thing I do to do this calculation is to write c with a shift of the numbers. I do not put the 1 below the 2, but below the 4, and then the 2 below the 6, the 3 below the 8, etc. And then subtracting column by column the very same way I've made before, it will sorry. Alone, and on the third line we get the value c, 2c minus c is c, and the first column gives 2, the second column gives 4 minus 1, which is 3, then 6 minus 2 is 4, 8 minus 3 is 5, 10 minus 4 is 6, etc. So we have a new expression for the value c, but remember that c is also the sum of all integers, and this last expression for c, 2 plus 3 plus 4 plus 5 plus 6, etc., only lacks the initial 1. So, in fact, in the last line, c is 2 plus 3 plus 4 plus 5 plus 6, we have simply that c is c minus 1, okay? So, if I just write things without being careful, I would be conjectured to write that 0 is minus 1 by subtracting the value c both sides of the equality, and then it hurts. Okay, sometimes allow you to do new things and be original, but if you go too far, then you will be hurt, because if 0 becomes equals to minus 1, then of course it's not really possible to do mathematics anymore, because every number is equal to every other one, and then, well, what could we do? No sensible thing could be said in mathematics if this was true. So the only way to avoid this is to decide which kind of things are authorized and which kind of things are not. And sometimes you can authorize new things, but even when if it's possible, you have to put some bounds on this, because otherwise anything will become true or become false, and very contradictory statements would be true at the same time. So this kind of thing would not be allowed. So, okay, consider the sum of integers, but remember that you cannot do anything that you want with it simply because you decided to define new things. And this is a part of what was quite amazing in Ramanujan's work, is, see back what he wrote. So in the beginning, it's it's only a few lines, very easy. Of course, he does not he doesn't provide all the details, but in his head, in his brain, everything was probably perfectly clear, and he did understood perfectly what he was writing and the context in which what he was writing was true, and that was he knew what he was doing, even if the formalism was not here. And to explain this formalism, I will not go into his deep procedure, which is now known as a Ramanujan summation, So it would be quite long, and I would like just to explain in which way we have to understand this kind of equality. And well, we don't have to take it to just writing it without being careful. And to understand what's going on, I'm going to use another context, but to understand what's really important here, it's p-adic numbers. I consider 9 plus 90 plus 900 plus 9,000, but etc. All the sum of all integers whose usual standard decimal expression starts by 9, followed by 1, then 2, 0, then 1, then 2, then 3 zeros. And I try to add them up all of them. So again, it's an impossibility. This sum has infinitely many integers, positive integers. So it should give us plus infinity, and okay, and we could stop. But so when I start the summation, I write 9 plus 90 is 99. Then I add the 900s, which gives me 999. Then 9,000s and 900s and 99, and etc. to infinity. So if I want to allow myself things, do a suspension of disbelief, then in infinity, when I add these numbers, all them up, then I would get a strange expression made of infinitely many nines and going to the left. Okay, because each time I add a new number, I put a 9 in the left. Okay, not on the right, but on the left. That's why the commas here are going to the left. If I was going to the right, that would correspond more to a decimal expression like 0.999, and that would be a standard real number. That would be equal to 1, by the way. But here I have something which is not a number, which is a formal expression made up of infinitely many nines going to the left. And I can say, I am willing to say that this expression is a way to express this infinite sum, 9 plus 90 plus 900 plus 9,000, etc. Right? Now, I would like to go deeper into this to understand what this strange expression could mean. Is it a number in the usual sense of it? Could it be that this corresponds to a real standard number? The same way to add try to add together all integer numbers and getting minus 1 over 12. So a way to see to what this expression could correspond, we can just add to it the value 1. In exactly the same way we add numbers, and we will learn in school to add numbers, since the nines are going to the left. If I add 1, I have to put the 1 below the rightmost 9 of my expression. And so this is not very difficult to do the calculation here. I start by 1 plus 9, which is 10. So I put 0, and I have a 1 to put it on the second 9, and then I have to add it to this 9, and 1 plus 9 is again 0, and I have another 1 to add it. I don't know if you write with the ones, the little the carry. if you write it the same place. Here in France, we write it here, but in some places they are written somewhere else. Well, you get the idea. And what's really important here is that each time I write a new 0, then I have a new carry, and it goes like this ad infinitum. And then my sum will only contain zeros. Okay. This is a quite strange point, and we have to understand what is infinity when we write this, because sometimes, well, I put a video on this in French, and on commentaries, many people say, well, but no, in fact, you don't have only zeros on in the result, because you have still a 1 to be put on the very left after the infinity of zeros. But of course, if we write infinitely many zeros on the left, then there is no way to put a 1 afterward, because there's no afterwards. We go to infinity, so there's no place to put a 1 in the extreme left. So we really have 0, 0, 0, just 0. So if a number which contains only zeros is simply the real number 0. So sorry. Oh, so I didn't put the right one. Sorry. So what the calculation tells us is that our strange expression here, 99999, going to the left, gives us the value 0, which is the real number x, for which x plus 1 is 0. It's just x equals to -1. So we would like to write that this number, 999 to the left, is simply -1. In another way, our sum 9 plus 90 plus 900 plus 9,000 plus etc. is simply -1. And it seems to be the very kind of strange result than Ramanujan's one. Infinitely many positive integers are added up, and it gives a negative number. So, is it true? And what can we say about this calculation? Is it true? In some sense, it is true, but of course, in some other, it is not. We can probably many of you already know about summation of geometric series. And if we as you know, I've written the formula here. For any number less than 1 in absolute value, then the sum of the geometric series of initial value a and ratio q is simply a over 1 minus q. It's a particular case of a general formula you probably know, and this only works if the ratio is less than 1. Here the ratio is 10. The initial number is 9, and then 9 times 10 is 90. Then times 10 is 900, etc. So I'm adding up the term of a geometric series, but with a ratio bigger than 1. So I cannot use this formula. But if I forget the condition, if I say, okay, let's do as if it was possible, then the initial number is 9, the ratio is 10, so I put an implication sign between brackets here, because it's not really an implication, it's not allowed by usual standard mathematical theorems. Then I would like to write, so the infinite sum of 9 times 10 to the n, which is another form for the very sum, the first sum I've put on the slide, is 9 over 1 minus 10, and indeed it is -1. 9 over -9 is -1. So it's another way to write this, to obtain the same thing, which is that 99999 infinitely many times to the left is -1. I proved it, not really proved, but I obtained by two different methods. The first one was a standard addition of numbers. The second one was an extension of a known formula. So it's quite convincing. It's quite convincing. But in fact, what's wrong, in fact, with this way of thinking is that, well, when I said 99999 infinitely many times to the left plus 1 is 000, then I said, well, what is the real number for which x plus 1 is 0? I said it's -1. But 99999 infinitely many times to the left cannot be considered as a real number. This is a new object. This is a perfectly new object because you know that any real number, any real number, if I can say so, can be written as, infinitely many digits, but not infinitely many digits in the left. In the right, after the comma, after the dot point. Okay. This is the standard results about the set R of real numbers. It's Archimedean. That means that there is, for any value x, I can find a bigger number, well, bigger than any other real number. This 99999 should be bigger than any real number. So it cannot be itself a real number in a standard way. That does not mean that it has no meaning. It has a meaning, but not the meaning of a real number. It is what is known as a p-adic number, with here p equals 10, so a decadic number, we can say. So in general, we consider many p-adic numbers for prime numbers p. Here, p is equal to 10, so it's not a prime number, but still it has a meaning. We can study this kind of expression, when you put infinitely many digits to the left, only when you define addition and multiplication, as you do for usual integers, you get p-adic integers or p-adic numbers in more general form. And there is a perfect sense to this. There's no problem. You can add this kind of expression. You can multiply them, and you will recover the usual properties of addition and multiplication, distributivity, etc. And everything will work fine. But doing this consists in creating a new world, not the same world as the real world. By real world, I mean world of real numbers. It's another kind of numbers. It's p-adic numbers. And in the p-adic world, yes, you can say 999 to the left is equal to -1. But it is not the -1 of real numbers. It's the -1 in the p-adic sense. That it's just that when you add 999 to the p-adic value 1, p-adic value 0. And the addition involved here correspond to the addition in the p-adic world. So there is a kind of homonymy. That means that words, well, different things said by the same word. When I say -1 here, in the equality on the top of the slide, I write something which is okay, which can be true, but we have to understand the -1 as being a p-adic number, a p-adic version of the -1. So we say -1 as we would for the usual real numbers, but it is not a real number here. As well as 9, 19, 90, 900, etc. And as the additions are also homonymous of the standard addition of real numbers, but none of this is real in the sense of real numbers. It is okay in another world. And this is why the equality 1 + 2 + 3, etc. is minus 1 over 12 seems so strange. It's not because it is true and it is paradoxical. It's not paradoxical at all, but it has to be understood as an equality which lives in another world. And the difference between what I'm talking about here for p-adic numbers and summation, the Ramanujan summation, is that for p-adic numbers, the difference stands in the fact that numbers are not the same. When I write 9, 90, 900, etc., or minus 1, the numbers involved here are not real numbers, but p-adic numbers. And for the summation, the Ramanujan summation, the numbers are real, but the way, the plus signs are not the same, and the equal signs are not the same. They stand for something different than the standard notation. And this is why we should never write something like the sum of the positive integers is equal to minus 1 over 10. And indeed, this is not the way that is written in specialized mathematics dealing with this. Is to put an R over the sum sign, because we have to remember that this equality does not occur in our usual world, but the world first seen by Ramanujan. And the R, of course, stands for his name, who since he was the first to deal with it. We can find some things in Euler as well, but he was the first to understand the world in which this equality is true. The world is not the real world always in commas. So, thank you for attention. I hope that it was. And if you, I will be happy to answer them.
Yes. Really, we are very confident that the calculation and the concept you have given are sure to trigger the young minds and motivate to take up deeper study and analysis and come up with newer concepts and solutions that will contribute to the mathematical world.
Sorry, I think I didn't get you. Did you ask me something? I could not hear you exactly.
Sir, can you hear me?
Can you hear? Yes. Yes, I can hear you now.
Vijay Kumar, sir?
Can you hear me?
Yes, sir. Yeah.
Mm-hmm. So, did you ask me something?
Sir, I can hear you. I can hear. Yeah.
So any questions that were posted or something, Vijay Kumar? Sir, I have a question now.
Yes.
I believe that when Ramanujan wrote about this this equation, particular equation that you showed, I think this could be done in relatively lesser age, not in later period, because it was recorded in his first notebook or second notebook. It was his notebook that he recorded this jotting. Now, at that time, do you believe that he could have thought about Riemann zeta function or something like that?
I'm not sure of this. It's already to Riemann zeta function. It's not clear for me. I think that he started to study it really deeper with Hardy. I'm not sure he was involved in it before, but not sure of this. Not sure of
Okay.
this. So indeed, another way to get this equality is to consider it as an extension of the Riemann zeta function, the
Yes.
analytic.
I mean, I guess that he could have worked the other equations pertaining to Ramanujan summation in much later period, extending this idea.
Mhm. Yes, it's later.
And what do you think Ramanujan's main contributions are to the modern mathematics?
Ramanujan, it's difficult. He
No,
made a
no,
lot of things.
you can just list a few, not mention about it. Just mention some of the headings that the other peoples and students may know.
Mm. So Ramanujan was mostly interested in number theory and the links between number theory and analysis. When we start to study number theory, we are concerned with prime numbers and greatest common divider or smallest common multiple, and etc. And we see arithmetics in a very algebraic way, and so this is what is said to be elementary arithmetic or elementary number theory. Not to mean that it's very easy, but it is quite a kind of internal way of doing doing this, of considering consideration like Bezout's theorem or Euclidean division, etc., or Euclidean algorithm. All of this is purely algebraic way of seeing number theory. And the more modern way to see number theory is to make use of analysis and complex analysis. And it's at the first sight, it's very strange to imagine that very complicated, very, very far away from integers or things like that. And this kind of tool is in general compulsory to get results on number theory. And this is one of the real important things Ramanujan did, is to go very deep in this idea. It was even not alone, of course, but he went on this idea very deeply. And he also had a way to understand numbers, which was very specific. He seemed to see, well, in general, when we see numbers, the intuition when, well, think about a number, in general, we will see something like a sequence of digits corresponding to their decimal expansion. And indeed, this is a good way to build, to define the set of real numbers, at least, with some problem, but easy way for conceiving the numbers. It's okay, but it's always depending on the choice of basis, general base 10 for us. And a much more deeper way of seeing number is a mathematical tool named continued fractions, which has a lot of advantages, also some issues, because it's difficult to add numbers with them. But still, continued fraction is a way to write numbers which is does not depend on any basis. It's a very different way of saying numbers, which provides deeper understanding of real properties of them. For example, if you write all the decimals of pi, there is no interesting pattern on them, and there is no reason for which there should be any specific pattern, because there is no link a priori between pi and the sequence of powers of 10. But the continued fraction expansion of pi provides much more, much deeper information on pi. How can we approximate it by simpler numbers? How is it far from rational numbers, and etc. But so continued fractions are a better way to, well, better, different way and deeper.
Okay.
And this was apparently the way Ramanujan had the intuition of numbers. And this is very, very strange, because it's very unnatural way of seeing numbers. Well, not unnatural, but very different and very difficult to have in mind.
Okay. Thank you, sir. Any other questions? Vijay Kumar, any other questions?
Still, we didn't get any questions, sir.
Sir, can you say something about your books, sir? Because we could not know what books you have written. Maybe you can talk about some of your books.
Well, I wrote indeed several books about mathematics. The one you mentioned before was the same kind of yours. I don't know. I don't remember the title you gave. But this was a book about inquiries linked to mathematics, and to find out who did the crime. Then you had to solve mathematics. It was so I wrote your book. I read your book. It was very, very good. My own was in the same vein in some respects, is that there were stories. There was not every time a murder or anything, but sometimes it happened in my own stories, and the aim was to make use of some mathematical trick that explained the story, and that the reader should understand, or at least understand that it was important to get into mathematics to understand what was going on in the story. It's a quite old book now. It's published 16 years ago, but it was a very interesting book to write, and maybe yours when you had the same feeling that there is a two part in each story. You have the first part that is very mathematical. Well, which kind of mathematics do I want to talk about? On the other side, which is more the story itself, the people in it, what happens to them, and put them together, put both hemispheres of the brain, stories and funny things and rigor and mathematics, and put them together. It's very interesting, because it's in general we cannot do both.
Where are these sources available, sir?
Sorry?
From where we can access the sources, the books and other material that we're talking about?
I think I can send one to you if you want. I can send the book. It's in French. Unfortunately, it's in French, but it was translated in Italian. But
very kind of you, sir.
Yes, I will send it. Well, I will take an address, and I will send one piece to you.
So what could be your advice to young students, sir? What could be upon
Sorry?
doing mathematics?
Sorry?
What is your advice to young students doing mathematics?
You mean
general advice upon how to enjoy mathematics, how to pursue mathematics.
Oh, to enjoy mathematics. So, well, mathematics is provides a way to see the world. It's not the only important way, but it's an important way. Logic, rigor, and these are important things in our lives. And we more and more with our technological world, we will need more and more mathematics. And it's sometimes it's difficult to understand that because mathematics are not very easy to see in our world because they hide themselves in some sense. When you use your mobile phone, or when just right now when me speaking to you, you are 10,000 kilometers from my place. How is it possible? There is technology, there is of course people who set up or organized it, but there is also a lot of mathematics, because without mathematics you should simply not invent the internet, invent our modern communications in every respect. And the more we go, the more we need them. And it's not it's for good to be painful for students. It's really useful in our world, and it is more and more important, and we need more and more mathematics. This is I'd say an economical answer. The most powerful economies in the world are those who develop science, technology, and behind science and technology you have mathematics. No way without this. There's no way to develop really. And there is yes, sorry. And there is also it's not the only reason for which mathematics are interesting. Mathematics are also about beauty. And I think a mathematician like Ramanujan understood this as a especially high level. He was not involved in rigor, in logic. He was not that kind of mathematician. But he wrote well. It is said, and you probably all of you know it. It is said that he was a friend with numbers. He understood their beauty in itself. And I remember when I came the last time to Chennai, you gave me very kindly a little piece of wood on which it was written a sentence of Paul Ortús, which is a famous Hungarian mathematician. And I don't remember the exact sentence, and I'm not at home, so I cannot tell it. But it is on next to my desk, and I read it very often. And it says, "Well, don't ask me why number are don't ask me about the beauty of numbers. This is wonderful, and if you don't get why, someone can tell you, because it's like a music. You can't say why music is nice. It's just nice because it is." And Ramanujan was one of them. He wrote formula. Why did he wrote formula? Not because it was paradoxical or new, but because it was nice, simply nice. It's like a painter or a musician. And this is a real important aspect of mathematics. It's not only about techniques.
Okay, sir.
Whether we're gonna prove by this way or this way, a very important aspect of the decision will be beauty. It is elegance.
Okay. So Vijay Kumar, do you have any more questions? If there are someone who can ask questions, please ask the speaker now. Madam Alamel, madam.
Yes, sir. Yeah.
If there are questions, you can ask. Otherwise, we can go for vote of thanks.
Sir, can you provide some of your references that you have worked on Ramanujan's work so that the youngsters may get motivated?
Can you say it again? Sorry.
Yeah. Can you please highlight your work on Ramanujan's work so that as a reference, if you provide it as a reference, so the youngsters may get motivated and they will start working on it.
Oh, I didn't row. Yeah, I can
No.
give
Can
you
you
some
provide?
references.
Can you hear me, sir?
Yes.
Okay. Can you provide some of your work as references so that the youngsters may get motivated and take up the deeper study and analysis, and they can come with your concepts and solutions, and they may contribute to the mathematical society by giving articles.
Oh, I can provide you some references, of course.
Okay.
I will send it to Sivaraman or yes.
Okay.
So I see a question here. Recent research going on. Oh, here, there are a lot of work which is made about Ramanujan's work. I think that there are still some formula we don't know how to prove them, because as I said, Ramanujan was not that interested in proving formulas. He felt formula more than he proved. And it was very long afterwards to understand how he could get into this kind of formulas. And I remember that there is a formula about pi, the number pi, which was quite important to him. He provided a huge formula, incredible, with the coefficients that you could not imagine that would appear in the formula. And so it was quite long afterwards to understand not only the formula in itself, but how Ramanujan could get it, which kind of tools could use to get this kind of very, very difficult formulas. And now, research about Ramanujan's work is mainly about analytic number theory. It's a generalization of a lot of things. I'm not a real specialist of Ramanujan in itself on this field of mathematics, but I know that, for example, a friend of mine, which is Laurent Laforgue, which is a field medalist in 2000s, I think, was working on generalization. Get these first successes in mathematics by looking deeper into Ramanujan work. So yes, it is still inspiring nowadays mathematicians. So about applications, yes, there is a famous saying of Godfrey Hardy. So he's a mentor in some way. Hardy in the field of number theory is that because I was sure that it could not be helpful to make war, and several years afterwards only, as you probably know, number theory became one of a crucial tool for cryptography, and one was an essential part of the success of America against Nazi Germany. So yes, it's useful. It's useful in many ways, but in general, whatever mathematician you consider of more than some decades ago, everything he did is necessarily useful nowadays, because almost all fields of mathematics is useful. It's kind of a strange thing. It's not intended to. And for example, the sum 1 plus 2 plus 3, etc. of Ramanujan is minus 1 over 12 has an impact in theoretical physics. It's called the Casimir effect, and can observe this equality in physics in some way. Again, in some way, it's not, well, you don't add up all the integers on seeing minus 1 over 12 in the end, but there is in some very specific part of physics an application of this very idea. So yes, application of Ramanujan mathematics exists as it exists for most mathematics since the beginning of mathematics. Oh, thank you very much for this.
Any questions, you can post it in the chat box.
That's all the questions, ma'am.
Okay. Thank you, Professor. We are very confident that the calculation and concepts you have given are very sure to trigger the young minds and motivate to take deeper study and analysis. Sri Srinivasa Ramanujan remains a great inspiration for us all to look further and further into the mathematical ocean. Thank you.
Thank you very much.
Now I request Mr. Raj Shankar, Trustee, Pi Mathematics Association, to thank our speaker. Please, sir.
Thank you. Good evening again. I would like to thank our chief guest speaker, Mr. Benoit, for enlightening us with his knowledge and spending quality time from his busy schedule. My view, today's lecture gave deep insight into the topic, also revealed some interesting facts. Thank you, Professor.
Thank you very much.
I would also like to thank Professor Sivaraman and founder of PMA for inviting senior professors across the globe for 133rd Ramanujan birthday. I want to thank the PMA team who really worked hard to make this event organized, especially Vijay Kumar for setting up this new streaming service. Also, thank all the students present here for paying your attention and learning. I would like to end my speech here. Thank you.